Today, on How It's Made. Kitchen knives, the product of cutting-edge technology. Mannequins, how it's made for dummies. Socks, the manufacturing process step by step. And hypodermic needles, time to inject some seriousness into this show. Any good cook knows that you're only as good as your tools, so using the right kitchen knife for the job is essential. From chef's knives and cleavers to boning knives, filleting knives, and paring knives, a serious cook buys only quality cutting utensils and stores them in a block to keep their blades sharp. Today's blades are truly a cut above the stone tools that cavemen used. Knife making is now a science, producing tools that really give you that edge in the kitchen. First, they roll out steel by the sheet from a big coil. Then, this machine called a press cuts out the blades with a punch. And it really does pack a punch. It brings 110 tons of pressure to bear in order to make these steel cutouts. Next, things get really hot. They roll baskets full of the blade cutouts into a high-temperature furnace. The blades bake at 843 degrees Celsius for 2 hours. This hardens the steel. Out of the fire and into the freezer. The blades chill out at sub-zero temperatures, minus 49 degrees Celsius, for 2 hours. This freezer is cooled by liquid nitrogen. Now we have what they call cold hard steel. Next, they douse each blade with water while a belt grinder smooths the back of the blade and sparks fly. Continuous water keeps the steel cool and hard while a sander smooths the back of the blade. Now a robot moves in. This robotic arm has vacuum grippers like an octopus. It picks up a blade by suctioning. Then it transports it to a grinding machine. The machine grinds the blade to give it that cutting edge. Water flows continuously through the grinder, again to keep the steel cool. The robot keeps everything moving, putting a paring blade through the grinder every 12 seconds. The automated process for this bigger blade is a bit different. This robotic arm holds the blade in a grip rather than through fast-acting suctioning. That's because it takes more time to grind this big blade called a cook's knife. So this arm holds onto this blade a few seconds longer. But if this makes you nervous, relax. The robot doesn't have a habit of dropping them. Some blades require a personal touch, like this Chinese chef's knife used for chopping veggies. The worker runs the blade over the grinding stone very carefully. This gives it a very thin edge. Then a laser burns the brand name onto the side of the blade. Next, a piece of wood goes into a clamp, and a router shaves it into the shape of a handle. The end of the blade now fits neatly into the handle. A worker clamps the knife onto a riveting machine. Those things that look like bullets on an ammunition belt are actually the rivets. The machine forces the rivets into the handle from both sides. The rivets lock together inside the handle so they can never be taken apart. Rivets are forever. Now they grind down any protruding steel from the handle. This makes the wood flush with the steel from the blade. The piece of metal that extends into the handle is called the tang. It gives the knife weight and balance. Finally, they hone the knife between two stone grinding wheels. With this kind of an edge, these knives will slice paper. But these knives will do their best work on the cutting board, where they'll make the cook's life easier and meals tastier, no matter how you slice it. They strike alluring poses in store windows, motionless models flaunting the latest fashions. For clothing retailers, mannequins are a vital sales tool. They come in fixed or flexible versions, the body's realistic or abstract, and they can be made out of a range of materials from wood to fiberglass. Meet Lady Swing and Mr. X. Not flesh and bone, but polyurethane foam. These fully flexible fashion figures start out as humongous blocks of soft polyurethane foam. Using a bandsaw, workers divide them into smaller blocks about the size of a large refrigerator. A worker creates a pressed wood mold using both a grinder and a sander to soften the inside. She applies a layer of putty over rough or damaged areas. This will harden and prevent the foam from clinging. She'll make separate molds for the arms, legs, and head and torso. A 1 square meter slab of foam goes on top of the mold. Then a slab of harder foam called a pattern on top of that. The foam layers in wood mold now go through what's called a pressure cutting machine. Pressure forces the slabs together while a thin blade slices the excess foam away. Exactly how much pressure the machine applies is a closely guarded trade secret. The foam arms pop right out on the other side. For the head and torso, they use a foam slab measuring 139 by 43 by 14 centimeters. And a foam pattern that includes shapes for breasts and a belly button, and grommets to shape the nipples. This foam pattern is impressionistic. These mannequins are not meant to be anatomically correct. Here's the pressure cutting machine close up. 9 rollers compress the mold, soft foam, and pattern slabs together, forcing them through a paper-thin opening and slicing away up to 15 centimeters of foam. True to form, Lady Swing pops up on the other side. Her flexibility is her raison d'être. She and Mr. X are often displayed on sports equipment like snowmobiles and bikes. Their manufacturer first named them in the 1970s, and the monikers just stuck. Workers inspect the mannequin and trim the excess material. They extract her easily because they sprayed the empty mold cavity with lubricant. Next, a worker assembles a half-centimeter thick steel skeleton to give the mannequin some structure. Workers will insert the skeleton between the half sections of the foam body. A welder fuses together 16 joints in the ankles, knees, thighs, hips, elbows, and shoulders. Another worker sprays slow-drying water-based glue on the skeleton and on the foam body sections that'll cover it. This will make them adhere together snugly. The hand skeletons are thin and pliable, like coat hangers, so they'll bend. A worker places the skeleton between the torso halves, positioning the foam so the edges meet evenly. These dummies don't come cheap. They sell for between $600 and $800 each, depending on the market value of the foam's main ingredient, oil. Still, that's a bargain compared to their more realistic-looking, but much less flexible, fiberglass cousins. They cost up to $2,000 each. After letting the parts dry and set overnight, a worker tests the limbs for flexibility. She joins together the lower leg portions. The skeleton protrudes at the heel so it can be secured to the floor when the dummy goes on display. Now here's a scene worthy of a horror movie. Using an electric carving knife, a worker slices off 6 centimeters from the front of the head. Ouch! She glues on a hollow face mask made of plastic using solvent-based glue for an extra strong bond. Next, they spray the mannequin with flesh-colored water-based glue. They sprinkle it with fine powder made of tiny cloth particles. This is called flocking. It takes 12 hours to dry and gives the mannequin a protective, fire-retardant skin. This factory's flocking comes in 18 different colors, from a variety of skin tones to several vibrant colors. Before Lady Swing makes her debut, a makeup session. Powder blush to color her lips and cheeks, and water-based paint on her eyes, lashes, and brows. They add a wig and voila! She's ready for her date with Mr. X. Socks are something we put on without thinking. But consider this. The very first socks were strips of cloth or hide wrapped around the feet. Imagine walking around in those. Thankfully, that's ancient history. And today's socks are much better for the soul. With so many styles and fibers for socks these days, it's no problem putting your best foot forward. But you have to step into this room of knitting machines to truly understand what a science sock making has become. Here's a machine with the top open so we can get a view of the knitting action. An automated whirling cylinder pulls yarn from spools through holes in metal spokes. Little hooks on the needles grab the yarn. The hooks have latches. The latches open as the hooks snare the yarn and close as they knit so you don't lose a stitch. As you can see, this machine knits socks a lot faster than Grandma, sometimes making over 360 pairs a day. As the layers are added, a sock emerges from a tube at the bottom. This knitting machine is fully computerized. It automatically switches to a different color of yarn to make a stripe or a company logo. Now the machine changes gears to make a heel. It does a half rotation instead of a whole one to knit the heel shape. The needles go up and down as the latches open, and the needles pick up the yarn, pulling it in. Knit 1, purl 2. Here it is in slow motion. This is about the speed at which a human could knit, but this machine normally runs at a speed of over 200 revolutions a minute. A tension mechanism moves back and forth, keeping the yarn from going slack and getting tangled. Now a sock shoots out of a vacuum tube, and a worker turns it inside out. She sews the toe closed and cuts off the extra fabric. Then she turns the sock right side out again, and it's sucked up by the vacuum. Next, the vacuum tube deposits the sock into a bin. The trapdoor on the end of the tube ensures that vacuum pressure isn't lost. But there's more than one way to close a sock toe, a more automated way. A worker slides the sock between two metal plates. Pressure holds them in place. Then a motorized conveyor system transports the sock to a sewing head. A blade cuts off excess fabric, and a needle goes up and down like an oil rig, stitching one row and then another as reinforcement. This automated system produces a finer seam than a sewing machine that's run manually. Now that the toe is closed, a robotic arm moves in and feeds the sock to a set of rollers. A blade pushes the sock down while the rollers turn the sock right side out. A vacuum chute fires the sock into a bin. Then it's on to the rotary dyeing machine. He loads 1,800 pairs or more depending on the size of the dyeing machine. The socks toss around in a bath of dyes, chemicals, and softeners. For athletic socks, they add antimicrobial treatment to the mix. It will help prevent fungus or bacteria that cause foot odor. Now they slide the sock onto a foot form made of polished aluminum that won't cause snags. The aluminum leg forms stretch the socks to the prescribed size as they travel down a conveyor belt into a boarding machine. The boarding machine is like a gigantic iron, and the heat seals the stretch in the nylon so the sock stays that size. Once out, a robotic arm grips the sock and pulls it off the aluminum form. It's called a stripper. Then, an automated rack with protruding pins collects the socks. The worker removes them a bunch at a time, and the socks are ready for packaging. And then, all you have to do is pull up your socks. A hypodermic needle is the proper term for a syringe and needle. It's used to draw blood or inject medication. This indispensable tool was invented back in 1853, but it wasn't until 1954 that mass-produced disposable syringes came on the market, developed for the vast immunization campaign against polio. A syringe may make you cringe, but the treatment it delivers could be a lifesaver. To make a hypodermic needle, they start with a flat strip of stainless steel. A milling machine rolls it into a tube shape. A laser welds the seams together. But what makes the steel stiff enough to use is something called cold work, in which they press the tubing through a die several times. This also slims the tube dramatically, so now you have a thinner, tougher tube. It takes about a couple of days to turn the stainless steel strip into a tube with needle potential. But it will have to be sharp to perform, and the next steps will focus on getting the steel tube to a point where it's more than just a blunt object. An electrically powered blade scores the walls of the tubes as rubber pads bear down and roll. This rolling causes the tubes to finally break at the score line. The tubes are being cut down to size, about 5 centimeters long. The tubes fall into a bin, a tangled mess. The bin, driven by air pressure, agitates, and this shaking motion straightens them out. An operator bundles them together with a plastic band, but removes a few to check the specs. This micrometer uses laser light to measure the outside diameter. The tube is supposed to be 2 millimeters, and it's right on. Next, a mechanically driven drum rolls super adhesive tape onto the tubes. The tape will hold the tubes in place as more work is done on them. They razor cut 12 centimeter strips of the tape tubes so that there are about 100 tubes per strip. Then they spray aluminum oxide on the ends of the tubes. This roughs them up so that the surface will be easier to work with. Now they place the strips of tubes into the grinding fixture, and then they snap it shut. Coolant flushes over the tube tips as the fixture moves across a grinding wheel. The wheel grinds through the tops of the tubes, shaping them into a rough point. This is only the first grind, so it's not yet needle sharp. Now the fixture rolls and rotates the tubes. Then it's back to the grind. The angle of the wheel is changed so that it sands the sides of the tubes. These two secondary grinds sharpen the tubes into a finer point. This is how they looked before grinding, and this is after, with their sharp needle tips. Now it's time for the big inspection. She pushes the ends of the needles with the back of her tweezers to make sure they're even, and then pulls out a needle for sampling. She measures the length of the grind. It should be a few millimeters long. Next, she sizes up the needle's outside diameter with a micrometer. Holding the needle between posts, it measures the space between them. Then she checks the inside diameter by inserting a plug gauge into the tube. Now she inspects a whole bundle of needles for irregularities or burrs. Using tweezers, she removes one for a close-up look under the microscope. Once they pass inspection, it's on to the big wheel or the automated assembly machine. Brass and nickel-plated fittings called hubs drop onto pins on the wheel. Then needles fall into the hubs. Metal fingers align them so they fit together precisely. The hub is the piece that will connect the needle to the syringe. Automated crimpers press the needle into the hub. Sheer friction bonds them. Now, two metal pads on the same wheel position the needle. A plastic sleeve drops down, encasing the pointed tip. Finally, a robotic arm lifts the needle off the wheel and drops it into a bin. The needles are now ready for you, but are you ready for them? If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net.